Hey everybody, this is Emmy Jakob and working with Courtney Brown, and this is our homework 13 and 14 for digital simulations, which is Engineering 460 at Liberty University. So for this homework, we were asked to create Brownian motion using kind of in the realm of finances. But before we get into Brownian motion, we have to create a box-Muller function. And to create a box-Muller function, based on our homework, which is in Appendix 6, the first things we need to do before we can do the Brownian motion, we were tasked to generate a standard random normal deviate using the polar box-Muller method, but we have to create a box-Muller function in itself first. So to do that, we create a function which can generate a random number using box-Muller, and then using that function, we can now put it into our MATLAB code over Brownian motion code, and then base that off of that to create our random numbers. So let's show you what that looks like in MATLAB. So the first part we want to do is create box-Muller random number generator. So to do that, again, we can create a function. The reason we create a function is because eventually we will call that function later, and it's easier to call it by box-Muller now to generate this function than to actually have to retype this every single time. So to do that, basically, we initiate that we want to make I Boolean. So if I is equal to 1, then we can set it to 0 to false, and then output the y. And in this else statement here, otherwise if it's not 1, it'll run through this iterations. Now this normally is taken from the Appendix 6, the book that it's written in, of the Monte Carlo and Digital Simulations in Finances book that we have. But what you're setting is from ij from 1 to technically infinity, but obviously MATLAB's not going to run to infinity, so we just did a really large number. We generate a random u, a random u2, and then an s based on those two random variables. So then if s is between 0 and 1, we can basically then output our b, x1, x2, and then end it out over here. So this gives me a random number. So once again, I'll just run this, and then through box-Muller we get a random number. So now let's go to the Brownian motion part of it. Again, the reason we ended up doing that box-Muller function was because we're going to call it here inside this for loop. So with Brownian motion, we're given actually 3 different examples that we want to run, or situations where we can set t equal to 100, n equals to 10,000. So t again is basically our period from 0 to 100, and then we can set different seeds and look at the way it looks on it. Again, and what we'll do is set I equal to 0, h is the period over n, 10,000. We can do a random seed, random number generator with a seed twister, sh b equals 0, and then we create a matrix of zeros basically of t, so 100 zeros long by 2, so 2 columns, 100 zeros long. And then we run through for j from 1 to n, which n is 10,000, going up by 1, we can run our box-Muller and end up running our basically random number generator again, and we run it through these next 2 functions to basically generate a plot. And what this plot will look like is as follows. Again, this is for t equals 100, n equals 10,000, and the c to 3671. Alright, that's our first one right there. Now running through those 3 scenarios that we have, we can basically generate plots based on those seeds. As you can see, just those differences in the seeds give us quite different data. So let's go to the next problem now. Now in the next problem we're going to look at geometric Brownian motion, and we're basically just going to add to what we did in that first part with just the Brownian motion by adding a few more variables and then changing the way we generate our graph. So we're going to look at expected growth rates, we're going to look at averages, volatility, and then a standard deviation. So let's go ahead and see what that looks like in MATLAB. So now this is the function for a geometric Brownian. Again, what I've actually done is taken and commented out, this is our Brownian motion that we've done before, where we looked at a period, we looked at our steps, and we looked at a seed for Brownian motion. Again, what we've added now is an average, we've added a volatility or standard deviation to it, and we've added a starting point now. And what you can do is we have 3 different options, or 3 different variants that we will run based on what the book asks us or the problem asks us for. So they all have the same period, which is 10. They all start at n equals 2000. The seed differs, and then the mu stays the same. The volatility changes from 0.02 to 0.04 to 0.08, and then we all start at the same spot. and most that's going to be the same exact what we've seen below here. The biggest difference you're going to see is right here in this definition of b. Instead of b, we've got that x equals this exponent x times e to the mh times sh times sigma times z, which is what will give us our geometric Brownian. So when we run that, we basically see right here. What you'll notice is the first one, which had the smallest volatility, was this blue line. The next one, which had the next larger volatility, would be the red line, and the next one after that was going to be this gold or yellow line that we see here. So that was basically being able to run our geometric Brownian, our Brownian motion, as well as knowing how to understand and run box Muller in MATLAB. Thanks for watching.